Most vision algorithms assume distant lighting. In this paper, we investigate the depth cues that can be extracted from uncalibrated near-point lighting. Our experiments were done by hand-waving an LED point light source in front of a scene viewed by a camera. In all of our experiments, we do not have the 3D position of the light source. The first depth cue we discuss is plane-scene intersections. We move the light source approximately in a line, as shown. By detecting brightness maxima at each scene point, we can produce plane-scene intersections. Here we color code those scene points that correspond to a particular intersecting plane. These results are similar to those of structured light, and we highlight each plane individually to produce a result similar to light striping. We now show results for more complex objects. Here we have a rough earthenware pot. Our method performs well both when the scene is glossy, such as this painted house, and when the specularities are sharp, such as this metal office desk. Here we show a wax candle illuminated by a laser pointer, showing subsurface scattering. We still detect plane-scene intersections, despite the complex appearance of this object. The second depth cue we investigate is depth ordering for homogeneous scenes. We move the light in a plane, as shown. We integrate the brightness at each pixel over time to produce a depth ordering of the scene with respect to the light source position. Bluish colors are closer to the light source position, while reddish colors are further away. We can also plot these depth orderings in 3D to provide a pseudo-depth visualization of the object. Here we show depth ordering for a plastic beach ball. Note that it has glossy specularities. Finally, we show a depth ordering scene for a statue with complex effects such as interreflections and self-shadowing. We render the depth ordering as a pseudo-depth in Maya using novel BRDF and lighting. Note that the hair and facial features of the objects are visualized well. We can obtain novel visualizations of the object without moving the camera. Here we have a wooden chair. We first show depth ordering by moving the light source in a left plane. Now we show depth ordering by moving the light source in a plane parallel to the image plane. Note that this is similar to traditional depth map results, where brighter pixels are closer than ones further away. Finally, we show ordering from the right plane. The third depth cue we investigate is mirror symmetries for homogeneous scenes. We reflect scene points across the light source path as shown. We match scene points with identical appearance over time to produce symmetry pairs. Symmetric pairs of scene points are marked with the same color. Our method produces reasonable results when the scene has sharp specularities, as in this office desk. In summary, we have shown how to extract novel depth cues from uncalibrated near-point lighting. These include plane-scene intersections, depth ordering, and mirror symmetries.